Saxon lesson 53b deals with angular velocity. Now, angular velocity can be confusing for some people, but I think that we can break it down in a little bit easier method of understanding in just a few minutes. So this shouldn't be that bad of a lesson for those of you who you start throwing in these words that sound a lot like physics and we get a little confused. It's not that bad. Okay, so first of all, let's understand what linear velocity is. Linear velocity is speed of the direction. If you remember that from any of your science in 9th or 12th grade science, both of them tell you that the difference between speed and velocity. Speed is a distance over time, and velocity is a displacement over time. So this has a speed with a direction as a velocity. So let's talk about what angular velocity means. Angular means with an angle, right? So we're talking about a speed with a direction, and we're talking about angular. Now, angular velocity is when you have like a spinning wheel. As it spins around, it is going at a certain velocity. Now, you understand that if I had two different wheel sizes here, and I looked at it and said I spun this one at a certain rate and this one at a certain rate, that if I was on the edge of this one, I will have gone further than the edge of this one, even if they're spinning the same rate. For those of you who remember playing on a playground as a kid, you would do the merry-go-round, and if you stood towards the center, you hardly carved out any distance at all. But if you went all the way towards the outside, you would go a lot further distance in each rotation. So in other words, there's a direct relationship to how far you are from the center of the circle to how far you go in relation to the center of the circle. Meaning, if I took this same and I said I went from here around to here versus from here around to here, these two distances are completely different, even though I've only gone through one rotation. So rotation is important with angular velocity, but so is the radius. And so when we look at velocity, we're going to convert between regular velocity and angular velocity. We're going to start with the angular velocity, and we've got an omega. This is a new symbol for us here. This is r omega equals velocity. R stands for your radius. Omega is the number of radians per unit time. Now, just as a recall, a refresh here, a radian, you have 6.28 roughly radians in a full circle. So if I took that radius and I laid it on here, I get about 3.14 through this side and another 3.14 through this side, so about 6.28, or to be precise, 2 pi. So 2 pi radians is one complete circle. Now, keep in mind a couple of things when we're working with this. If I had this, the example is going to be a wagon wheel, and that's why I have that drawn here. This wagon wheel is, even though it spins, the outside of this is making direct contact with the ground. Hopefully it's not spinning. This is why if you drive a vehicle off the pavement and you look at the tire track that's left, it's not just a spun hole. It should have, if your tire was making traction with the ground, it should be as if you took the tire and just stamped it into the ground and then picked it up, right? Except that you have a line of those stamps as they all went around. So that as they go around here, they're all making contact with the ground only in one specific spot at any one given moment in time. It's not spinning against the ground. That would be if you didn't have traction. So this right here, if I wanted to take this wheel and say it started here and rolled through, I could take the outside rim. If I took that out and unrolled it, it would be the exact same distance as the circumference would be. So when we're talking about the velocity, how fast it's going, it will be the circumference, right, in a unit amount of time. Well, what is circumference? Circumference is 2 pi times my radius, right? And so I say 2 pi r is a circumference, and then I multiply that by, or divide that by how the unit of time that I'm going, and I will end up with this same idea of r omega. It's just hidden inside of the formula. We're going to go through the 52.2 example here, and then we're going to look at it with a little more of a logical base on where we're getting this. So to begin with here, they said that a wagon has a radius of 14 inches. That's the wagon wheel. And it's revolving at 40 revolutions per minute. Now I went ahead and put it in, that's RPM. You see that with engines. That's what the tachometer on your car, when you rev that engine, you're watching that tachometer, and it's times 1,000. So if you're at 2, it's 2,000 RPMs, rotations per minute. It's how fast that engine is spinning, right? It doesn't tell you how big the engine is, doesn't tell you how powerful it is. It only tells you that noise that you hear is that rev is how many times it's rotating per minute. The next thing that they said is that how fast is the wagon moving in miles per hour? Well, miles per hour is not an angular thing, right? We're not talking about the miles around a wheel. That would be really weird. What we're doing is we're saying if I were to unwind this wheel, right, how fast is it going along this path? So when I do this, I say, well, 1 revolution equals 1 circle, and 2 pi is 1 circle. So I can do my unit conversion from 53.A and say 40 revolutions per minute times 2 pi radians, or 2 pi r over 1 revolution. Okay, radians and radius, very similar there. Okay, so that ends up with 80 pi r over minutes. I wrote down what I knew, minutes, I'm going to go to hours, pi is 3.14, the inches to feet, and feet to mile. And I set up my conversion factor like I did in the unit conversions by saying 1 foot is 12 inches, 1 mile is 5,280 feet, 60 miles is 1 hour. Then I start canceling any units that I can, and I'm left with 1.06 pi miles per hour. Now, this is where the confusion is for a lot of students. When you see pi, we've always thought 3.14 until we started working with pi and we said, oh, let's convert it to degrees, and so we say pi is 180. How can it be both 180 and 3.14? Now, this is something that's a little aside from the book. If you've understood this to this point, you can pretty much ignore me. But what we're saying here is that when we're working with converting how many radiuses are on the outside of the circle, there's 2 pi all the way around. But if I'm converting to degrees, I'm saying how many parts of a full circle, 360 degrees, would there be? So yes, 180 does equal pi, or 360 degrees equals pi, but pi also is 3.14, so pi, or 2 pi around the circle. So I'm going to use my 3.14 in here for pi. Okay, and that's what I have to understand what I'm doing here. I'm not converting to degrees. I'm actually saying how many radiuses are there. Well, I've got a 14-inch radius. And so I converted this. 1 foot is 12 inches, and that's going to convert it to feet, miles, and 5,280 feet. That's going to convert this into miles. And then I want to get it out of minutes into hours, and I get 1.06. I put this in here on purpose. If you use your pi key times 1.06 instead of 3.14, you will get 3.33 miles per hour. And that's, the book left it in a simplified version of this. My mind doesn't work that way. I like to see, if they said how many miles per hour it is, I want to see how many miles per hour it is. This is 3.33 miles per hour. So you can see a 14-inch wheel. It's not a very big wagon wheel, right? And it's spinning at 40 revolutions per minute. So in 1 minute at a time, it's going through 40 times all the way around, which is pretty quick, right? 40 times per minute. But how, if I did that, I would say, well, how fast is it getting there? And that's my rate. It's going about 3.3. Now, I'm going to take the same idea and we're going to break it down into not necessarily the formula that the books showed us, but we're going to just use some logic here. And to me, this helps the understanding. You can use this formula. I use this formula myself. However, this is the understanding. 1 revolution is 1 circumference. If you keep that in your head, it'll make more sense. 1 revolution is 1 circumference, right? Because I can't unwind that there. And they said a radius is 14 inches. So they said from here to here is 14 inches. Well, if I wanted to find out what 1 revolution was in inches, I would say 2 pi r is 1 circumference, or once all the way around. So I could say a circumference, all I did is do the math here for us. 2 times 14, which is 28, times pi, 87.964 inches is 1 revolution. Well, that makes sense. That means that if this right here, 1 time around on this wheel, is 87.964 inches. But they said it was going 40 revolutions per minute. So I went ahead and I said, well, if a revolution is the same as a circumference, which it is, I can say, therefore, 40 times 87.964 per minute. And this is going to be what my rate is in inches per minute. This makes more sense in my mind is that to explain it, because really what I'm saying is this is how many circumferences per minute, 40 circumferences every minute. So I'm going 3,518 inches this way in every minute. Now it's just a unit conversion problem like I would have before, and I say, well, I want to go from minutes to what, hours? Okay, well, I know that's 60, so 60 hours or 60 minutes equals 1 hour. And I go inches to feet, so 12 inches equals 1 foot. I go from feet into miles, 5,280 feet equals 1 mile. And I set up my conversion units the same way. There we are with the inches canceling, the feet canceling. I'm left in miles. My inches are gone. My minutes are gone, and so I'm left with 3.3 miles per hour. This is the same answer. Really, we're doing the same thing. The key is that when you're looking at a formula like this, velocity equals r omega, you're just simply hiding in the fact that a full circle is a circumference. That's what a revolution is. And I say how many radians per unit time. All I'm doing is breaking that into the two formulas that it would have come from in the beginning. And so you can work this either way that makes sense to you. Of course, if you memorize this formula, it makes it really simple because you're just plugging it in. Or you can logic your way through it and say, hey, I'm going to go from revolutions per minute, or which is circumferences per minute, right? And then convert it that way. It works the same, and you're free to use either method you like.